Good afternoon. My name is Bart and Romeny. I'm going to talk about the Raspberry Pi 5 and Mathematica, a STEM creativity powerhouse. The Raspberry Pi is a STEM student's dream. STEM stands for Science, Technology, Engineering and Mathematics. It's a small single board computer developed in 2012 by the Raspberry Pi Foundation, and today we have the Raspberry Pi 5, and it can interact with an amazing array of sensors, motors, displays, joysticks, cameras, you name it. It has 40 GPIO, general purpose input-output pins, Bluetooth, USB ports. You can connect a webcam to Wi-Fi. And version 5 is now finally fast enough to run Mathematica perfectly. It has a quad-core Cortex CPU, it has a nice video core, and it has PCIe support. That means very fast I/O. And because Mathematica is 3 GB, you need 8 or 16 GB of RAM, and it's not expensive, or reasonably $100 for 8 GB version and $154 for the 16 GB. But you get a full-blown computer that you can really use as a desktop. And Mathematica is free on every Raspberry Pi. It's also free for most university students. And for all STEM students from high school to PhD on any other computer, it's only $7.35 per month. It's cheaper than Netflix. You can see that on the Wolfram official page. And you install Mathematica very easily. And if you want to see how everything works, look at this website. And what we go do is integrate sensor reading and driving with low-level Python, and we use high-level Mathematica for very fancy analysis and visualization. This gives a super boost to projects. For some of you it will be new. One of the very nice things is the 21st century coding. So for example, I can add here images. I just drag them from another, for example, from another window, from an example of web browser. And if you now say manipulate, you can manipulate phi. Phi is the angle over which you rotate it, and now you can very easily rotate it. So now you see a couple of things. You have images in your code, you have Greek letters in your code, you can manipulate everything. It's very 21st century. Here you see that everything is interactive in a sense that you can use algebra. Well, everybody knows if you expand this, you get x squared plus 2xy plus y squared. But if you make this n, and you let n run from 1 to 100 in steps of 1, you get this same slider again. It's a Java applet generated by this manipulate. And now you can do interactive algebra. And all this runs now on your Raspberry Pi. And of course, you can add all kinds of graphics, plots, you name it, Fourier transforms, everything can be manipulated. So you can change the amplitude here, you can change the frequency, you can change the phi. So explaining things and playing with things is now a one-liner. And Mathematica is very strong for scientific notation. You use the escape key before and after, so escape P escape gives you the Greek notation for the pi. So the escape you use for creation of symbols and control to modify symbols. So if I say x hat 2, that's x squared. But if you now say x control hat 2, you really get this nice superscript notation. Mathematica is easy to learn. You see some interesting links right here. Sensors. We will have a look how easy it is to run Mathematica together with Python to read the temperature, pressure and humidity and display the results on an LCD display. We have a €1 cheap sensor, the BME280, and a small 4-line display. And what we first need is to read some packages, and we do this in Python. There's a resource function Python package install, and it is successfully done. Now we start a Python session. That's an external session, and you see that this is a virtual environment. And in this virtual environment, it's called session, we're going to do an external evaluation of Python code. And here we see the code with the address and initialization of the bus. And we do exactly the same for the read the sensor. And now what we're going to do is this is a definition, we make a function. So with this delayed assignment, we define a function that is called in Mathematica read sensor. So if we use this now with square brackets, that's the function called in Mathematica, we see we can do a read sensor. The same we can do for a write, and now we have the initialization again external evaluate in this session. You see we have address 27 and this is the LCD, and here we make a function that is writing. And this function has 4 arguments, date string, temperature, because that's what's gonna write. So we make the date string and we're gonna write it on the display, but it is nice to display this every second and we get an update. And here is what the display shows you. And because we have Mathematica, we can do some really nice thing. Here, for example, we can make a girl blush if we hit the sensor. When I now push the sensor, you see the sensor here on the bottom, you see the following movie. Another application is to use compile and make things really fast if it's computational pretty extensive. This is a beautiful script written in the JavaScript. It was discovered by Vitaly Karov and written by a Japanese author. And he found an amazing formula. And this is the formula. And it generates for a given time a coordinate x, y. Pretty complex. If you look at the traditional form, and you just ask Mathematica, write this, and traditional form, you see, wow, that's pretty something. How can we calculate this? And we go calculate this in 160,000 positions. So that's actually a lot of calculations. So let's see what happens in time 0. Oops, we get a very complex formula, and Mathematica is very precise. So it keeps this signs of this ratio like it is. So we need to make, of course, first real numbers. And we do that by giving one of the numbers a dot. So if there's one real number, now you see we get real numbers. Let's take how long it takes to calculate all these numbers and at 10 time moments. This is how it takes 4 seconds on a Raspberry Pi. And now we do it numerically. Well, 3.2 seconds, so it doesn't make that much sense. But let's compile this function. Well, compilation is very nicely documented. The documentation, by the way, in Mathematica is unsurpassed. It's the best in the world. I can easily say that. I have 35 years of experience. It's amazing. So let's make this into input form so we can easily see it. Okay, now it is in a nice form. And we put that in the compile function. You see that right here. And now we have a compiled function, and let's put it in there and calculate how long does it take if I use this compiled function. Well, 75 milliseconds. How much faster is this? 43 times faster. That's nice. Okay, let's make it as a movie. And now you see that the jellyfish is swimming in your aquarium. The next couple of examples I'll do a little bit faster because you have the full notebook and can do everything on your own Raspberry Pi or on your laptop. Geogebra is a well-known function for high school students, 30 million users, and you can do all kinds of geometric visualizations and calculations. But the Mathematica, it is extremely easy to plot almost everything. Here we see a circle through 3 points. It's a manipulate function. And now, because I have what's called a locator, I can easily move any point. And you see, I can move it all the way at any direction. You can show the bisectors. Here's the first one, here's the other one. And now you can see interactively. You could even put logos in there. You see how fast it is on a Raspberry Pi. You can also easily work with neural networks. And here we do some interactive object detection with a webcam camera just connected to the USB of my Raspberry Pi and the neural net Yolo 5. In the Wolfram neural network repository, that's a website that is just beautiful. It has lots and lots of neural nets that are completely put into Mathematica, and everyone has given examples on how to use. And here we're going to use the Yolo 5, and please explore it. It's wonderful. If I give the command net model, you see all these nets. There are quite a few. If we ask how many, what is the length of this net model, there are currently 166 fully trained networks available. So we're going to load this network, and this is now loaded from the web. We take as image current image, and current image is a Mathematica command that means read the webcam. And you see, hey, it's looking at my desk, and you see it detected the keyboard, even a remote and a mouse, and it has found these, here is the screen, these rectangles, keyboard, TV, mouse, and remote. And when we put dynamic, we get 1 frame per second, classification and detection. And that on your Raspberry Pi. It's pretty impressive. It's extremely easy in Mathematica, even on your Raspberry Pi, to make very complex neural networks. Here's an example. I have a whole bunch of layers, batch normalization layer, a ReLU layer, logistic sigmoid, etc. And I call them 1, 2, 3, 4, 5, and you just say connect 1 to 2, and the output of 1 to 3, 2 to 5, etc. And the input is a vector with 20 elements. You let Mathematica do the whole thing. It's an uninitialized network, and here you see the whole network. And the nice thing is that if you click on one of those, you see exactly what it does. So this is a catenate layer. It has all these vector sizes, etc. You see 20 goes in, 50 goes out, 20 plus 20 plus 20 is 60. It's very convenient. And if you have a whole bunch of them, really complex, it doesn't take too long, you get the perfect network. You see, no matter how complex, you get exactly what you want. It's extremely convenient, and I think this is the most beautiful neural network design and work with I've ever seen. And suppose you want to see what happens inside the network. Let's load the network, the Wolfram identify, and I image identify, and you see it has lots of layers: convolution layer, ReLU layer, pooling layer, convolution layer, and all these layers have numbers. And now what we can do is let's manipulate, and we take from the net model and we put as input a cat, the layer number n. And n is the layer number, goes from 1 to 30 in steps of 1. So let's do that. Now we get to manipulate, and now we can see, okay, let's make this a little bit more convenient. Layer 4, layer 5, layer 6, layer 7, etc. And it's now very easy to see what all these layers, what they do. And as you see, with one command on your Raspberry Pi 5. And by far the best book I know about learning neural networks and doing everything interactively in Mathematica is this book on machine learning by Etienne. He worked for 7 years in the Wolfram the neural network group. He was architect of most of the networks, and he's an excellent expert and a good tutorial teacher. So I can really recommend to have a look at this book. You will be pleasantly surprised. Let's do some computer vision on our Raspberry Pi. And let Mona Lisa smile. So we use here the radial basis transform, and we put it in a dynamic module. So we put some points on her face, the tip of the nose, and some points on the corners of her mouth. These are the coordinates. We call that sources. And now in the manipulate, we're going to do an image transformation. And we use the radial basis transform, and specifically the thin plate spline. It is a 2D interpolation function. And if I move a point, it interpolates all the points that are surrounding it. So let's have a look. Let's generate Mona Lisa. This is Mona Lisa here. And now we can say we put a point here, and we can easily change her face. And you see that thousands of pixels are interactively. So we can very nicely change everything in her face, and you can put as many points as you like. And this, of course, if you have all these talking faces in neural networks under the hood is exactly what happens here. You have phase deformation in this way, but now you have a very nicely mathematically understood way. Let's look at some visualizations. And on YouTube, 3 Blue, 1 Brown is a very famous tutor who visualizes a lot of beautiful math interactively. He's still writing on the whiteboard, but he's making beautiful graphics. And let's see how we can do this in Mathematica. So we're going to do the same. We look at this function. We're going to maximize x squared y on the circle. X squared plus y squared is 1. So let's make this plot. Okay. The first function, x squared plus x squared y, you just make a contour plot. Here it is. We don't want the mesh, so we say mesh is false. Then we say, let's make the style a little bit bluish. So we make this RGB color. And we make a specularity on it. Now we get some highlight points. Okay, let's do some lighting. That means we we have this strange shadow here, but we put the lights now better. We have an accented lighting. We added the cylinder, so now we have two functions, you see here between two brackets. And we add this function x squared plus y squared is 1. And that's a cylinder because z is not specified of all values of z. But we make now the cylinder opaque. So we have opacity 0.1. And now you see I have the opaque cylinder. And of course, everything you can rotate in 3D. And the boundary style is just, this is graph number 1 and that's graph number 2. So you just say the graph outside of 1 is 0, but between 1 and 0 is red. So let's have a look. And now you see I have a red contour in between them. It's a little bit, line is somewhat coarse, so we make a little bit more plot points and we make the line thick so we see it better. And now you see I have a thicker line. And if we put some arrows, you just say with these kind of arrowheads, we make a tube. We have here the nice set of arrows and you combine them into your graph. And now you have a very nice complete thing with the arrows. And this is exactly what 3 blue, 1 brown was doing. And the final code, if we put it all together, it's just a few lines, and that's right here. You can even go further and say, well, I can put a texture on it. And what texture? Well, plug in any image. And now you can make a cloud on this graph. You see it is all in the same. And now we have a texture on our graph. In Mathematica, it's so easy to make it beautiful. Actually, everything you want, you can do. And if you say this line, the red line here, you want to, internally it's represented as a line representation. But if you say change line into tube, and that's exactly what you do here, it is calculated as a tube. And now you have a tube, but now you can say, let's make this tube radius larger and smaller, and we do that in a manipulate. So you can even say, I have now a manipulate, and if you say, I want the opacity a little bit less, and now you see more of the cylinder, all interactively. But if you want the tube radius bigger, just make the tube radius bigger. And you see it. A weather station. Very easy to make a fancy GUI for a weather station. In Mathematica, I can just say, read from a website the weather data in Eindhoven, read the temperature, the pressure. Here I read from the local Dutch weather forecasts, the weather maps, the wind radar, the humidity. You read the date string. Here from a time sprayer website, I read the moon image. And here is the result. And you see that it is nicely updating. The clouds are moving. You see the temperature inside, outside, the pressure map, the pressure over the last 14 days. It's very easy to make a weather station like this. Here's another nice example for STEM students if you want to visualize what is the physics of bouncing balls. There's a beautiful website from called Matthias Research. It's called 10 Minutes Physics, and it has a very nice implementation of ball collision handling. It's written in HTML. I used the Notebook Assistant to convert this HTML code into Wolfram language code. And it did it, and it was pretty nice. And this is what I got, because it very nicely said if the radius is smaller than the distance between them, make the velocity minus the velocity, so it bumps, it goes the other way around. And this is the interactive simulation. If you are an advanced STEM student and you want to see how is fluid flow actually calculated, well, that goes with partial differential equations, and very famous ones are the Navier-Stokes equations. And they look like this. Well, in Mathematica, you can just program it like this, like you have from the textbooks. And here you see, let's take a geometry. So we make a region, and we put some fluids to the left inside, and here we have two outlets. And we're going to see how are the flow patterns in there. We put some conditions. It's called Dirichlet conditions, but that means what is the velocity here and how much is flowing in and what is the velocity when it goes out. So we put these conditions in, and now we enter the Navier-Stokes equations and have a look how beautiful this is in Mathematica. This is a differential operator, that means ddx, ddy, and the Greek letters, rho, you have the velocities, u and v. I'm not going to explain all this, but you see how very elegant you can enter these Navier-Stokes equations. And now we let them calculate with a finite element method, point by point, and we do a numerical differential solve value. That means it solves these partial differential equations in a numerical way. And it does this on your Raspberry Pi. And wow, we get a beautiful visualization. The flow comes in here, you see turbulence here, and if you now change the geometry, you can make any other geometry and it calculates the flow lines. Let's have a look now how incredibly precise Mathematica is. We have this amazing number, and this is found by Mr. Pisot. Let's calculate 10,000 digits of this number. Mathematica does that, and it goes really fast, even on your Raspberry Pi. Hey, this is an amazing number. It has an incredible amount of zeros. How could you find a number like this? And this shows how you can use parallel processing on your tiny Raspberry Pi, because it has 4 GPUs, and I put the resource monitor here so you can see what the CPUs are doing. This is the Raspberry Pi system monitor, and you just say to Mathematica, let's test if we have a prime here, and this means this hash sign is a number that goes from very high, 9601 to 12,000, and it's going to parallelize that. And Q is a question mark, so this means is it a prime? And do this then for these high numbers, powers of 2. So if you run parallelize, Mathematica does it all automatically. It launches the subkernels. It can see that there are 4 kernels here. And now you see on the system monitor that all 4 are being active. And now you see that it is 76 runs over these 4 kernels, and they all run at the same time at maximum power. And it gives us a long list of about 2,000 false, 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 true. And of course, it's not so easy to see, but let's Mathematica do the whole thing. We can say in this res, which is a long series, where is the position of a true? Because we started at 9601, we add 9600, and now we find the positions, and hey, there are 3 prime numbers in this series. And in conclusion, you can now do everything in really modern style 21st century coding. And for STEM students is the advice, get your Raspberry Pi 5 or a student license and realize that this is cheaper than Netflix. For parents, if you are retired on schools, give or use a Raspberry Pi for fun and a lot of learning. And most important, check the resources. The documentation of Mathematica is the best in the world, and it's fun to keep learning. You discover so much. There's an amazing amount of public resources, thousands of cool demonstrations, and if you want to more know about this lecture, look at the notebook. On a personal note of me, I've been a STEM student my whole life, and Mathematica played an important role. I really feel privileged. I could work with Mathematica notebooks for 35 years. Notebooks, not other coding. Brain-inspired computing for medical imaging, big data was my field. It made my career. So, spread the word of these STEM delights in the Raspberry Pi communities, social media, schools, and beyond. And have fun!